Hello students, welcome to FosterJEE. So, this is our fourth lecture of electrostatics. In last lecture, we have done few problems based on electric field and a problem is given to you for homework based on Coulomb's law. So, this is our problem. Let's discuss the statement of this problem. Charge positive Q is distributed uniformly over this rod. And the length of rod is L. A charge Q with magnitude minus Q is placed at a distance A from the one end of rod. The mass of this charge is m, and we are asked to find the velocity of charge minus Q when it covers half of the distance, that is when it reaches A by 2, that is in the middle of this distance A. Now let's see how we will solve this problem. Now we will draw a rod here. Now if this is our charge, let's suppose we take an element at a distance x from the charge. This element is very small with thickness dx. If this distance is a and this charge is minus q, and a total of capital Q is distributed uniformly over the surface or length of rod. Hence we can write the charge density of the rod is dq upon dx. Now since the charge is uniform, that means charge density is constant at every part of the rod. So can we say the average is the total charge upon total length? Yes. So the point is, when a charge is uniformly distributed over the rod, this is constant for any section of rod, and hence we can write lambda as total charge upon total length. Hence the charge carried by this element will be dq equals to q upon L dx. Now if this is a point charge and this is also a small point charge, so the force of attraction between these two point particles will be written by Coulomb's law, and that is F equals to kq dq upon x square. Now note that we can't use d small q here because it would be mathematically incorrect. So let's take it capital D, so capital Q. Otherwise we would have done the integration q dq, and that would be very incorrect. So we have to keep something to differentiate the charge on this body and this charge. Now what is dq? dq is the small charge carried by this particle. So we will put the value of dq here. We get kq capital Q upon L dx from this equation upon x square, and this becomes kq upon L dx upon x square. Now if this is a very small force, we can write it df. Now df equals to kq capital Q upon L dx upon x square. Now we have to integrate this equation, so be careful about the limits, that when x was a like this, no element of the rod was being covered. So the total force of attraction between these two bodies will be 0. Why? Because x is a. And when x becomes a plus L, that is this whole length, then whole length of the rod will be covered, and in that case the force would be total force, and that would be F net. So integrating this equation, we can write net force F net equals to KQQ upon L. Now this integration becomes minus 1 upon x, limits a to a plus L, and putting the limits we get KQQ upon L. This becomes 1 upon a minus 1 upon a plus L. Now there's a catch in this problem. Now we are able to get the force of attraction between these two bodies when the distance between one end and the particle is a. But now let us suppose this distance is some variable, that is s. Why? Because initially the particle was here at this point, and it will start moving here, and the distance between this end of the rod and the particle will keep on decreasing. So let us suppose at any instant the distance becomes s and the particle is here. We can say when the distance between one end and this charge is a, in that case force was this, that is dependent on a. But when the distance between one end of the rod and the charge is s, in that case net force would be, rest all is constant, we will just replace a by s. I hope this is clear. Now since the charge is moving, it will have some acceleration, and if the net force is this, we can write mass into acceleration, which is also net force, equals to KQQ upon L, 1 upon S minus 1 upon S plus L. Now we can write acceleration as dV by dt equals to KQQ by L, 1 by S minus 1 upon S plus L. Now note that in this equation only S is variable, rest all the items are constant. So in order to get the velocity, we have to eliminate this term, that is time, since this equation has three variables. One is S, one is V, and one is T. So we cannot integrate it right now, but we have to replace this term in terms of either V or S or both, so that it becomes easier to integrate this equation. Now we know that if the distance between them is s, so the rate of change of distance will be the velocity of this charge, because velocity of this particle means the rate at which this distance is being decreased. So it's clear that the velocity of charge is ds by dt, and from this equation we can get dt equals to ds by v. Putting this value in our finite equation, we can get m v dv by ds equals to kq q by L 1 by S minus 1 by S plus L. Or we can also use the chain rule in calculus from this step, as we have discussed this in one of the previous problems also, that this can be written as m dv by ds times ds by dt, and we can see this ds by dt is nothing but bv, so this becomes mv dv by ds, and hence these terms are same. So we can also say that the time term is being eliminated, so it becomes easier to integrate this equation. Now rearranging the terms in this equation, we can write v dv equals to kqq upon ml into ds upon s minus ds upon s plus l. Now we will simply integrate this equation. Now note that when s, now it should be clear that s is the distance of this charge from one end of the rod at any time. So initially s was equal to a, because initially s was this much. So initially the charge was at rest. So when s was equal to a, the velocity was 0. And from the question, we have to evaluate the velocity when the s becomes half, that is a by 2. So we need velocity v when s becomes a by 2. Now simply we will integrate this equation. Now we will get v square by 2 equals to kqq by ml times, we know the integration of, now first of all we will see that this integration sign gets inside because this term was constant. So this becomes a to a by 2 minus integration of ds upon s plus l, a to a by 2. Now we can solve this. We know the integration of 1 by x with respect to dx is ln x. So this becomes ln s, and the limits are a to a by 2 minus ln of s plus l, and the limits are a to a by 2. Now solving further, this becomes kq by ml ln 1 by 2 minus ln a by 2 plus l upon a plus l. Now if you have doubt in this integration, you should watch the previous lecture in which such type of integration is being explained. Hence we can see this whole term v square by 2 becomes kqq upon ml. Now this can be written as minus of ln2. Why? Because log a to the power b is log ba. So using this property, this 2 goes up and it becomes 2 to the power minus 1, and minus 1 comes out. Minus, this can be written as ln a plus 2l upon 2 times of a plus l. Also from this term we can see a plus 2 the denominator is 2 times of a plus l, that is 2a plus 2l, that is a plus 2l. Hence we can see the denominator is larger than the numerator by this amount, because in the numerator we have to add something to get the denominator, so denominator is smaller. Hence this whole term is less than 1. So we will use this property again here and get v square by 2 equals to kqq upon ml ln twice of a plus l upon a plus 2l minus ln 2. Now also we know that log a minus log b is log a by b. Hence we can use this property on this term, and this becomes v square by 2 equals to kqq upon ml ln of twice of a plus l upon a plus 2l whole upon 2, and this 2 and this 2 gets cancelled out, and v square becomes v square by 2 equals to kqq upon ml ln of a plus l upon a plus 2l. Hence the velocity v becomes root over two kq q upon ml ln of a plus l upon a plus 2l. Now there is a mathematical mistake in this equation. What? That when log of a by b or anything log of x, when x is less than 1, then y equals to log x, so y is negative, because if inner term is less than 1, the whole term becomes negative. Similarly, we can see the denominator is larger than the numerator, so this whole term is negative, and inside square root we can't have any negative item. So where's the error? So remember, while writing the force, we have written only the magnitude, but one charge on the rod, that is this dq, is positive, but this term, that is this charge, is negative. So either we have to apply negative over here, or we will just plug negative over here, so that this equation becomes mathematically correct. So this minus is because of this charge q. So now it is perfect mathematical equation, which is our answer. Now if you are able to get this answer correctly or even partially correct, then it's very good. But if you are unable to tackle this type of problem, then don't worry. In our course, we will be discussing many such type of advanced problem, which will be sometimes above the level of JEE Advanced. Through those videos, we will be able to learn how to think, not how to get an answer. For that, you can purchase our course, in which, along with completing all the theory and the basics of the chapters, we will be having many dedicated videos for only questions. So check out our courses and please download our app FosterJEE from Apple Store or Google Play Store. Now, coming to this question, we can see the length of this problem. It is very, very large. And it took us more than 15 minutes to solve this problem. But what if I say we can solve this particular problem in 4 to 5 minutes? Now, how is that possible? That will be possible by using the concept of electrostatic potential energy. So our next topic is electrostatic potential energy. After completing this topic, we will again come to this problem and we will see how the length of this question gets reduced. Now, in very simple words, we can define that suppose we have a charge Q, Q1 and another charge Q2. So, we know that this charge will create some electric field around it and this charge will create some electric field around it. Of course, now we know that these are electric field lines and they won't interfere or they won't cut with each other. So, just to show, I'm showing only few electric field lines. So, we know that let's suppose they have some distance r between them. So, we know that these both charge will interact with each other. That is, one will exert force on another and vice versa. So, they are able to do this because they have some energy associated with it, which is termed as electrostatic potential energy. Now, we know that electrostatic force is conservative. Electrostatic force is conservative. So, if any force is conservative, it has some potential energy function associated with it. So, this is very standard result of physics that if a force is conservative, it has to have some potential energy function associated with it. For example, gravitational force is conservative. So, we know that gravitational force is conservative and hence we are able to define gravitational potential energy. In similar way, we will define electrostatic potential energy. Electrostatic potential energy. It is denoted by U. Now, let's find out the expression for U. Suppose we have one charge Q1 here and suppose another charge initially it was at very far distance, that is, let's suppose it's at infinity. Now, recall from the previous lecture that when one charge is at infinitely large distance, will this charge be able to impact this charge, or will its electric field reach this charge? The answer is it will reach, but it's very, very, very small, very, very negligible. So it's almost no effect on other. Now, let us suppose by some external agent we started it to move towards this charge Q at very, very small rate so that it doesn't gain any kinetic energy. Uh, let's suppose initially the charge Q2 was at infinity and this is Q1. Now suppose by external agent this charge come to this distance and now the final distance is R. Now what is the work done in moving this charge from here to very, very near to this? Let us suppose this is dr. Now the work done will be force into distance dot product. Since we are moving along the line of action, cos theta will be 0. So this is fdr cos theta, and cos theta is 0, so it becomes fdr. Hence dw is fdr. Now what is F? When the two charges are at a distance r, the force of electrostatic will be kq1 q2 upon r square. Putting this in our equation, this becomes dw equals to kq1 q2 upon r square dr. Now integrating this equation, when the charge was at infinity, that is r equals to infinity, since there was no attraction or interaction between the two charges, to move at very, very large distances, we don't have to perform any work against any forces because there was no force. So the work was 0. But when the final displacement or distance between them is r, we have to perform some work. Let's suppose that work is w, which is our point of discussion. So this becomes w, this becomes kq1 q2. The integration of this is minus 1 upon r, and the limits are infinity to r. Now putting the limits, this becomes k q1 q2 minus 1 upon r minus 1 upon infinity. This becomes 0. So this becomes minus kq1 q2 upon r. Now this is the work done to bring q2 from infinity to a distance r. But by the definition of conservative force, we know work done by any conservative force is a negative of change of its potential energy. Remember, this is not valid only for electrostatics, but it's valid anywhere where conservative force are being acted. This is valid in gravitation or electrostatics, or in any case where conservative force are being acted. Note that this is not applicable for non-conservative forces like frictional force, and magnetic force, etc. Now, this is the only reason why we don't define any type of potential energy associated with frictional force or magnetic force. But since electric field, electrostatic force is a conservative force, we can write minus of its change in potential energy equals to work done, and work done we have calculated as minus k q1 q2 by r. This becomes minus k q1 q2 upon r. Now this becomes delta u equals to k q1 q2 upon r, and this is u final minus u initial. And again, since initially the charges were at very far distance, so there was no force between them and hence no interactional force or energy. So initially the potential energy was 0. Finally, so uf or u is k q1 q2 upon r. Hence we are able to get the expression for potential energy between two charges. And note that since electrostatic forces electrostatic force is conservative, its potential energy is a state function. Now what does state function mean? State function means that suppose initially the charge q1 is here and the charge q2 is here. Now let's suppose this charge is fixed, but this charge we are moving. Now suppose this was initial point A and this is the final point on which we have to move charge q1. Now how many paths are possible to move from A to B? The answer is infinite. We can move like this or like this or like this. But assuming both charges are like, the forces on every point will be in different directions, like here in this direction, here in this direction, here in this direction, here in this direction, due to this force, due to this charge, sorry. But and also the distance is traveled by this charge to travel from three different paths will be different. But what is same between them is that the change of potential energy between the 2 points, that is delta u, that is equal to ub minus ua, is same for all paths, whether it is 1, 2 or 3 path. The change in potential energy is always same. So this is the meaning of state function. Now, as we know, the charge between two charges q1 and q2, the forces of interaction, the electrostatic potential energy U between the two charges is k q1 q2 upon r, if the distance between them is r. Let us suppose this distance is r12. So the potential energy between them is k q1 q2 upon r. What if we have more than 2 particles? Let us suppose we have 4 particles. There we have Q3 and here Q4. What will be the total potential energy of this system of 4 charges? So, first of all, we know that potential energy will be the combination of all the different pairs different pairs of charges. What does this mean? This means that total potential energy of the system will be, first we have to choose this charge and calculate its interaction from these 3 charges. So a number of equations will be 3 due to first charge plus, now we have to log Q2 charge and its interaction with Q4 and Q3. We don't consider this interaction because initially when we were considering from Q1, we have already considered from Q2 and that will be same. So due to Q2, the total number of equations are 2. Now we will log Q3, and since these 2 charges are done, we won't consider from this effect and it becomes only one equation plus 1. Now logging Q4 makes no difference. So the total number of equations that will be drawn is 6. Now let's see what are those 6 equations. That is U12, that is the potential energy between 1 and 2 is KQ1 Q2 upon R12. Similarly, U34 is the potential energy between Q3 and Q4, that is KQ 3Q4 upon R34 and so on. Now the total potential energy, that is the potential energy of system, will be U12 plus U13 plus U14 plus U23 plus U33 no 24 plus U34, that is 6 terms will be occurring. And writing the complete equation, we can write the total potential energy of the system is KQ1 Q2 upon R12 plus KQ1 Q3 upon R13 plus KQ1 Q4 upon R14 plus KQ2 Q3 upon R23 plus KQ2 Q4 upon R24 and finally plus KQ3 Q4 upon R34. This is our final potential energy of the system. Now, just a trick that to calculate how many terms will appear to calculate the potential energy of a system of many charges. So we know that by counting we have concluded that this system will have 6 equations. But since we know we have 4 charges and each charge or each interaction will be the resultant of the 2 particles. So we have to select 2 particles from 4 particles, and the number of ways of doing it is the total number of equations. So what is that? By mathematical PNC, permutation and combination, we know it is 4C2. That is, we have chosen 2 particles from 4 particles, and C becomes C. Why C has come and not P? Because in this order doesn't matter. Like Same same interaction will be if we consider 1 or 2 or 2 or 1. So 4c2, and the value of 4c2 is 4 factorial upon 2 factorial and 2 factorial, which is 6. Now suppose we have a system of 6 charges which are very randomly placed. Let's suppose these are Q1, Q2, Q3, Q4, Q5 and Q6. So the total number of equations that will be withdrawn from this system, so the total number of terms that will be appearing in the total potential energy of the system will be 6c2, which is 6 factorial upon 2 factorial 4 factorial, which is 15 terms. Student can also count if they want to. Now, so while counting the number of pairs in a system of n charges, that would be nc2 or n into n minus 1 upon 2. Now, let's take up a problem just to understand all that we have discussed today. So the question is, we have two charges Q2 and suppose this is also Q2, and we have a charge minus Q1. So we are given that the distance between these two charges is A, and initially Q1 was very far, so that the electrostatic force of attraction was very small, but it was just sufficient to start a motion. We have to find out when it comes from very far, what is the speed of this charge when it reaches this point. Now there are two ways of doing this, as we have studied. First is by Coulomb's law. Initially, by Coulomb's law, we will let that this charge is at a distance, any general distance is y. So we will draw the free body diagram of this charge and write up the forces. So let's suppose this angle is theta, so this angle is also theta. So we will write, if the force is Fe, we will write 2Fe cos theta is equal to the net force, and that will produce mass into acceleration, and the acceleration would be m dv by dt. So we will replace, by chain rule, we will do v dv by dy into dy by dt, and we know that dy by dt is the rate of change of distance, that will be its velocity. So we will write mv dv by dy and 2Fe cos theta. By putting the values of forces and cos theta angle in terms of other parameters, we will find the velocity. But we can see this method is either tedious and time taking, but we will see how we can solve this problem with the help of potential energy. Now, since initially the particle was very far, so the net potential energy of the system at that time would be, now how many particles are there? there are three particles. This particle, and this particle. So how many terms will come? 3C2, that is 3 terms. So let's write these 3 terms. First of all, the interaction between these two charges. What will be that? K Q2 Q2 upon A plus. Since this charge is very far, so their potential energy is negligible. So we will write 0 plus 0. So initial potential energy of the system is KQ1 KQ2 square upon A. Let's this our first equation. Now finally, when the charge comes at this place, we can see now the distance between minus Q1 and Q2 is A by 2, and this distance is also A by 2. Now what will be the final potential energy of the system? That would be K. First we will write potential energy of this Q minus Q1 and this charge Q2. So that would be K Q1 Q2 upon A by 2. But since we are dealing with energies and that is a scalar quantity, so sign becomes important in this, because in this we can't just correct the signs by seeing the direction. Scalar quantities have no direction, so we have to put minus sign for minus charge, that is Q1, plus what will be the interaction between this and this? That will be same, like K minus Q1 Q2 upon A by 2, plus there would be interaction between this Q2 and this Q2. So that is K Q2 Q2 upon A, because the distance between them is A. So simplifying this equation, we'll get U final is equal to minus KQ1 Q2 2 upon A minus 2K Q1 Q2 upon A plus KQ2 square upon A. Now, hence the change in potential energy becomes U final minus U initial, that will be minus 4K Q1 Q2 upon A plus KQ2 square upon A minus KQ2 square upon A, because initially the potential energy was this. So this gets cancelled out, and change in potential energy becomes minus 4K Q1 Q2 upon A. Now we know by the definition of potential energy, we can define minus U or change in potential energy as negative of work done, or work done will be negative of change in potential energy. Hence the work done will be minus of minus 4K Q1 Q2 upon A, which is 4K Q1 Q2 upon A. Now from mechanics, we know that work done on any particle will be converted to kinetic energy increment, that is final kinetic energy minus initial kinetic energy. This is the statement of work energy theorem. Work energy theorem. It says that work done by any force will be the change in kinetic energy of the particle. Since initially the charge was just very far and it just experienced some of the interaction the net kinetic energy would be very small. So we can take it as 0. So initially it was 0. Now let us suppose this has mass m. So our equation becomes 4k q1 q2 upon a is equal to half m v final square. So v final square will be 8k q1 q2 upon ma, and hence vf becomes root over 8k q1 q2 upon ma. Hence this is the velocity of this charge when it reaches from very far to this point. Now we can see mathematically using the potential energy concept makes the solution very small and easy. Now, as discussed in the starting of the lecture, we discussed a problem, this problem. Let's see how we can easily do it with the help of potential energy. Now, the question was, there's a rod which is fixed, and here we have a point charge. Its mass is m and charge is minus q. The charge capital Q is uniformly distributed over its length L, and initially the distance between this end and this charge is a. We have to find the velocity of this charge when it comes at the middle, that is at a by 2 distance. Now, using electrostatic energy concept, we can see initially that we have to calculate the total electrostatic potential energy due to this rod at any point. Let us suppose at a distance x from this rod, we have to calculate the total electrostatic potential energy. Suppose we take up an element at a distance s, and that element is ds. Since this particle is very small, we can treat it as point charge, and the potential energy du for between two point charges is given by k q1 q2 upon s, that is the distance. Now, since the total charge q is uniformly distributed, hence we can say linear charge density is total charge upon total length, and this is also equal to dq upon capital dq upon ds. So dq becomes q upon l ds. Hence this element contains charge dq, which is equal to q upon l ds. Now du is k q1, the value of q1 is minus q. We have to put along with signs, and the value of q2 is this, that is q upon l ds upon s. This becomes minus k q capital Q upon L ds upon s. Now integrating this equation, this term is constant. Now when s is equal to x, in that case no element of the rod was being considered. So in that case the potential energy of interaction will be 0 at s equal to x. And when s is equal to s x plus this total length, so in that case full this distance is being considered, and hence whole rod will be covered. So the total potential energy that we need due to whole rod is U. And when S is equal to x plus L, let's solve this equation. It becomes U equals to minus KQQ upon L ln integration of ds upon s is ln s. The limits are x to x plus L. Hence, total potential energy of interaction between the rod and the charge will be minus kq q upon L ln of x plus L upon x. Now note that this is true for any distance between the charge and the rod. So initially when the distance is a, we can see potential energy is ui is equal to minus kqq upon L ln, in place of x we will write a and rest is same, and u final when the charge comes at this position, that is the distance between them is not x but a by 2. So the total potential energy becomes kqq upon L ln, in place of x we will replace a by 2 plus L upon a by 2. So change in potential energy becomes u final minus u initial, and that is minus kqq upon L common becomes ln a by 2 plus L upon a by 2 minus ln a plus L upon a. This is equal to minus kqq upon L, and this becomes ln a plus 2L upon a minus ln a plus L upon a. So this becomes kqq upon L, and this becomes ln a plus 2L upon a plus L, because log of a minus log of b is log a by b. Now we have calculated change in potential energy as this. Now by the definition of potential energy we know work done will be negative of change in potential energy, that is negative of this. So simply this negative term will wipe off. This becomes kqq upon L ln a plus 2L upon a plus L. And from mechanics we know work done by unit charge, or the force between the unit charge and the rod, will be converted to the kinetic energy of the particle. Since the mass of particle is m, so it becomes half mv square. Now rearranging this equation, we can write v square is equal to 2kq q upon ml ln a plus 2L upon a plus L, and hence the velocity becomes v is equal to root over 2kq upon ml ln a plus 2L upon a plus L. So this final expression, you can compare it with the earlier which we have derived using Coulomb's law, and this expression is exactly the same as that. And also in this, since we have considered the sign of q, there is no mathematical error also here. So this equation is perfectly fine. Hence we got one more method to solve the problems of electrostatic using electrostatic potential energy. Now if you want to see many more questions and comparison with many methods like this, you can check out our course And that courses are at a very reasonable price. That will include many dedicated videos for many tough questions like this, which will help you boost confidence and tackle problem involving many concepts in physics. And for more practice problems, please download our app from Apple Store or Play Store. And now we'll meet in our next lecture. Thank you.